In this lesson, we will cover the design of big, fast modern routers. Here's a picture of two modern router chassis. On the left, we have a picture of the Cisco CRS-1, and on the right, we have a picture of the Juniper M320. The M320 has for some time been used at the border of the Georgia Tech network between Georgia Tech and the rest of the Internet. Here's a picture of a couple of line cards that go into these chassis. These kind of look like network interface cards, except the ports are special. Instead of terminating Ethernet, these ports terminate high-capacity fiber links. As you can see, these cards are actually a whole lot bigger than your typical network interface card as well. And as a result, these chassis are often anywhere from 3 to 6 feet tall and can fill up an entire rack. There's a significant need for big, fast routers. Links are getting faster. Traffic demands are also increasing, particularly with the rise of demanding applications such as streaming video. Networks are getting bigger too, in terms of the number of hosts, routers, and users. So there's a perennial need to design big, fast routers, particularly in Internet backbone networks. The rest of this lesson will focus on how a router works, in particular how it goes from the process of taking a packet as input and sending it on to where it needs to go. The Internet's routing protocols, of course, are responsible for populating the forwarding tables on a router. But once those tables are populated, the router still has the hard job of taking a packet as input and ultimately getting it to the appropriate output port so that the traffic can proceed en route to the destination. Let's take a look at a generic router architecture. As a summary of basic router function, a router receives a packet. It then looks at the packet header to determine the packet's destination. It looks in the forwarding table to determine the appropriate output interface for the packet. It modifies the packet header, such as decrementing the time to live field and updating the IP header checksum appropriately. And finally, it sends the packet to the appropriate output interface. The basic I/O component of a router architecture is the line card, which is the interface by which a router sends and receives data. When a packet arrives, the line card looks at the header to determine the destination, and then it looks in the forwarding table to determine the output interface. It then updates the packet header, and finally sends the packet to the appropriate output interface. Now this drawing shows just a single line card, but in fact, when the packet is sent to the output interface, it must traverse the router's interconnection fabric to be sent to the appropriate output port. So in fact, we can zoom out from that depiction of a single line card, and what we have is a bunch of line cards that are all connected via an interconnection fabric. Each of these line cards has a lookup table, the capability to modify headers, and a queue or buffer for packets as they enter and leave the line card. In other lessons, we talk about several important questions, such as how big queues should be and how lookup works. In the rest of this lesson, I'll discuss important decisions in router design, such as the placement of lookup tables on each line card and the design of the interconnection fabric. One important decision in the design of modern routers was to place a copy of the forwarding table on each line card in the router. Well, this introduces some complications in making copies of the forwarding table. Doing so prevents a central table on the router from becoming a bottleneck at high speeds. Consider an alternative where the router has only one copy of the forwarding table. In that case, all of the line cards would need to be performing lookups on a central table, which involves communication across the backplane as well as many more lookups against a central table. So while distributing the forwarding table across line cards prevents a central table from becoming a bottleneck, early router architectures did not place the lookup table on each line card, and as a result, when packets arrived at an individual line card, they would induce a lookup in a shared buffer memory, which could be accessed over a shared bus. But this shared bus, of course, introduces a bottleneck as well as contention between the different line cards that may be all performing lookups to the same shared memory. The solution, of course, was thus to remove the shared memory and instead place copies of the forwarding table on each line card. In summary, an important innovation in the design of these routers was to eliminate the shared bus and place the lookup tables on individual line cards. The second important decision is the design of the interconnect, or how the line cards should be connected to one another. Now, one possibility is to use a shared bus, but the disadvantage of a bus for the interconnect is that it could only be used by one input-output combination in any single time slot. What we'd like to do is enable input-output pairs that don't compete to send traffic from input to output during the same time slot. For example, 1 should be able to send to 4, 2 to 6, and 3 to 5 all in the same time slot. The solution to this problem is to create what's called a crossbar switch, or sometimes is also called a switched backplane. In crossbar switching, every input port has a connection to every output port, and during each time slot, each input is connected to 0 or 1 outputs. The crossbar is often depicted as follows. So if 1 wants to send to 4, we could connect the input to the output in that time slot, and now this row and this column is occupied, but we could connect 2 to 6 and 3 to 5 in the same time slot without introducing contention. So the advantage of this design is that it can exploit parallelism by allowing multiple packets to be forwarded across the interconnect in parallel. But of course, we also need proper scheduling algorithms to ensure fair use of the crossbar switch. Let's take a quick look at what this algorithm needs to achieve. We'd like the crossbar switching algorithm to achieve what's called a maximal matching. Conceptually, we have a router with n inputs and n outputs, but of course the inputs are also outputs. It's just easier to think about the inputs and outputs being separate when we talk about the switching problem. Now, in each time slot, we would like to achieve a one-to-one mapping between inputs and outputs, which is a matching. And our goal is that the matching should be maximal. So in a particular time slot, we might have a certain set of traffic demands, or traffic at certain input ports that is destined for certain output ports. And our goal is, given these demands, to produce a matching that is maximal and fair. Now, given demands for a particular time slot and the resulting matching, notice that certain demands were not satisfied. These packets that arrived at inputs must wait until the next time slot to be forwarded to the appropriate output port, because they couldn't be matched in the same time slot as those shown here. Remember that there must be exactly a one-to-one matching between any inputs and outputs in a particular time slot. Most router crossbars have a notion of speedup, whereby multiple matchings can be performed in the same time slot. So for example, if the line cards are running at, say, 10 gigabits per second, then running the interconnect twice as fast would allow matchings to occur twice as fast as packets would arrive on the inputs or be forwarded from the outputs. It is thus common practice to run the interconnect at a higher speed than the input and output ports. Just speeding up the interconnect does not solve all problems. Note, for example, that in this set of demands, we have packets arriving at this input port destined for this output port. But if there's only a single queue at this input, the packets that are destined for the output port, circled in orange, might actually be blocked behind a set of packets that are destined for other output ports. So even if we could induce a speed up at the interconnect, certain packets may be blocked in the queue by packets ahead of them, destined for other output ports. For example, if we have packets arriving in this queue, destined for the orange queue, at the front of the queue, then even with the speed up, there may be packets that are sufficiently far behind in the queue that they're waiting behind the orange packets. What we'd like to be able to do is perform matchings to allow these packets to be sent to the output ports and not have to wait for the entire queue to be drained of packets destined for the orange output port. A solution is to create virtual output queues, where instead of having a single queue at the input, we have one queue per output port. This prevents packets at the front of the queue that are destined for a particular output port from blocking packets that could otherwise be matched to other output queues in earlier time slots. Let's now talk about scheduling and fairness. Now, we talked about, in a crossbar switch, the process of matching input ports to output ports. The decision about which ports should be matched in any particular time slot is a process called scheduling. There are two important goals in scheduling. One is efficiency, which is to say that if there is traffic at inputs destined for output ports, the crossbar switch should schedule inputs and outputs so that traffic isn't sitting idle at the input ports if some traffic could be sent to the available output ports. Another consideration in scheduling is fairness, which is to say that given demands at the inputs, we want to make sure that each queue at the input is scheduled fairly for some definition of fairness. Now, defining fairness is tricky, and there are multiple possible definitions of fairness. Here we'll look at an important fairness definition called max-min fairness. Now, to define max-min fairness, let's first assume that we have some allocation of rates across flows xi. Now, we say that this allocation is max-min fair if increasing any rate xi implies that some other xj that is smaller than xi must be decreased to accommodate for the increase in xi. So in other words, the allocation is max-min fair if we can't make any one of these flow rates better off without making some flow rate worse off that's already worse than the flow rate xi. So the upshot results in small demands getting exactly what they ask for, and the larger demands splitting the remaining capacity among themselves equally. More formally, we perform this procedure as follows. We allocate resources to users in order of increasing demand. No user receives more than what they requested, and users that still have unsatisfied demands split the remaining resources. Let's consider an example for max-min fair allocation. Let's suppose that we have a link with capacity 10 and 4 demands, 2, 2.6, 4, and 5. Now obviously the demands exceed capacity, so we need to figure out a way of allocating rates to each of these demands that is max-min fair. First, note that 10 divided by 4 is 2.5. But this is not a good solution because the first user only needs 2. So the first user would have an excess of 0.5 under this allocation. So what we want to do is take this excess of 0.5 and divide it among the remaining 3 users whose demands have not yet been fulfilled. This would yield an allocation of 2, 2.67, 2.67, and 2.67. But now user 2 has an excess of 0.07, so we take that excess, divide it among the remaining 2, and that gives us our final max-min fair allocation. Note that this is called max-min fairness because it maximizes the minimum share to each user whose demand is not fully serviced, in this case the third and fourth users. As a quick quiz, let's try doing a max-min fair allocation. Suppose that we have demands of 1, 2, 5, and 10, and link whose rate is 20. Please give the max-min fair allocation across these 4 users. To compute the max-min fair allocation, we take 20 and we divide it by 4, which yields 5. But the first user only needs 1, which yields an excess of 4. The second user only needs 2, which yields an excess of 3. So in this case, the max-min fair allocation is easy. We simply take this excess of 7 and give it to the only user whose demand is not yet satisfied, resulting in the max-min fair allocation of 1, 2, 5, and 12. Now how do we achieve max-min fairness? One approach is via round-robin scheduling, where, given a set of queues, the router simply services them in order. The problem here is that packets may have different sizes. So if the first queue had a huge packet, and the second queue had a little packet, and the third queue had a medium-sized packet, then servicing these queues in order obviously isn't fair, because the first queue would effectively get more of its fair share because its packet just happened to be bigger. An alternative is to use bit-by-bit scheduling, where during each time slot, each queue only has 1 bit serviced. This, of course, is perfectly fair, but the problem is feasibility. How do we service 1 bit from a queue? A third alternative is called fair queuing, which achieves max-min fairness by servicing packets according to the soonest finishing time. A fair queuing algorithm computes the virtual finishing time of all candidate packets, which are the packets at the head of all non-empty flow queues. Based on these virtual finishing times, fair queuing compares the finishing times of each queue and services the queue with the minimum finishing time. So the queue whose packet has the minimum virtual finishing time is serviced.